In early 2025, a research team released a paper boldly titled AlphaGo Moment for Model Architecture Discovery, describing an AI system that they claim can create entirely new neural network architectures and evaluate them through a complete cycle of controlled experiments. They claim that this framework is the first demonstration of artificial superintelligence for AI research. This system, named ASI-ARCH, operates without human supervision. It generates its own hypotheses, converts them into working code, trains models on large datasets, and measures their performance against competitive baselines. The authors present this not as a step forward in automation, but as a shift from simple optimization to genuine autonomous innovation, arguing it moves beyond the limitations of past systems and allows for AI research to accelerate beyond the bottleneck of human cognitive capacity. This extraordinary claim has ignited a debate in AI research. Supporters see it as an early, tangible sign that scientific discovery itself could become a closed-loop process driven by AI, potentially shattering the human limits of research. Critics, however, question whether the results are large enough to justify such a monumental framing, whether the evaluation was designed to favor the system, and whether the presentation as an AlphaGo moment crosses the line from scientific paper into marketing hype. I'm going to unpack how ASI-ARCH works, trace the experiments it ran, and dive into the controversy over whether this is truly an inflection point in AI research, or a claim whose significance is still uncertain. Neural network architectures are the fundamental blueprints that determine how an AI system processes information. They're the frameworks of modern AI, defining how data flows through layers, how those layers transform it, and how the network learns from examples. Even seemingly small architectural changes can have profound effects, altering a model's performance, efficiency, and the range of tasks it can handle. For decades, the design of these architectures was considered a form of art, an exercise in expert intuition and painstaking trial and error. The field progressed through a series of landmark architectural breakthroughs that repeatedly reshaped the AI landscape. Consider the introduction of residual connections in the residual neural network, or ResNet, architecture. Before ResNet, training networks hundreds of layers deep was a monumental challenge, plagued by the vanishing gradient problem, where the signals used to update a model's weights effectively disappeared as they were propagated back through the layers. The simple yet revolutionary idea of adding skip connections that allowed the networks to bypass layers and directly reuse previous outputs solved this fundamental problem, making it possible to train much deeper and more powerful networks. The next major leap forward came with the transformer architecture. This innovation replaced the traditional recurrence and convolution mechanisms that had long dominated natural language processing with a new approach based on attention mechanisms. This shift allowed models to process entire sequences of data in parallel and weigh the importance of different words in a sentence, paving the way for large language models that dominate today's AI landscape. These advances, while seemingly inevitable in hindsight, all started from human insight, which was then tested and refined through repeated experimentation. But the pace of this progress has always been constrained by a fundamental human limitation. Researchers have to choose which designs to test, and their choices were often guided by intuition, existing literature, and the collective wisdom of their field. This reliance on human decision-making has created a central bottleneck in the acceleration of AI progress. In the late 2010s, the field saw a glimmer of hope with the rise of neural architecture search, NAS. This offered a partial automation using machine learning to explore a vast, predefined space of possible architectures and improving them through systematic exploration. This method proved its value, producing architectures like Google's EfficientNet, which achieved higher accuracy with fewer parameters than many human-engineered networks. However, NAS was still fundamentally confined to human-defined search spaces. The possibilities were mapped out before the search began. The system could move quickly within those boundaries, but could not propose architectures outside of them. It was a powerful tool for optimization, but it lacked the capacity for true invention. The ASI-ARCH paper presents its system as fundamentally different. The core claim is that it does not search within a fixed design space. Instead, it generates new architectural concepts without predefined boundaries. It then writes the code to implement them, and then tests them in a continuous, self-improving loop. Supporters see this as a radical step towards removing the central human bottleneck in AI research. But critics argue that the novelty of these designs has not been fully proven, and that without independent replication and verification, it's hard to know whether the system is truly expanding the design space or simply reassembling familiar ideas in a more complex way. The central question is shifting from how to design better architectures to who or what should decide which designs are worth pursuing. Can AI truly escape the confines of human-driven research and generate scientific breakthroughs on its own? The authors of the ASI-ARCH paper frame their work in relation to one of AI's most famous moments, the 2016 match between AlphaGo and the Go world champion Lee Sedol. With more possible game configurations than there are atoms in the observable universe, Go has long been considered a test of human intuition and creativity, and was long believed to be a game that could never be mastered by brute force computation. Early computer programs could handle casual players, but were no match for world-class experts. AlphaGo changed that forever. AlphaGo is a powerful AI system that plays the game of Go. It was developed by Google DeepMind and works by combining two distinct deep neural networks with a sophisticated search algorithm called Monte Carlo tree search. The policy network analyzes the game board to suggest the most promising next moves, effectively learning from a vast amount of human and computer play to narrow down the immense number of possibilities. The value network evaluates the positions on the board to predict the winner of the game. It provides a quick and powerful heuristic that allows the system to judge the strength of a position without playing out every possible game to the end. These two networks work together to guide the Monte Carlo tree search algorithm. The policy network helps the search focus on the most promising branches, and the value network provides a quick assessment of their potential, enabling AlphaGo to explore a far greater number of positions than a human player while still maintaining the strategic intuition required to play at a master level. In the second game of its historic match against Lee Sedol, AlphaGo played move 37, a decision so unusual that professional commentators initially thought it was a profound error. It went against centuries of established Go strategy, but as the match unfolded, it became clear that the move was a stroke of strategic brilliance, a deep, counterintuitive insight that completely changed the board and ultimately led to AlphaGo's victory. The AI had developed a strategy no human had ever considered, revealing a part of the game that was invisible to us. For the ASI-ARCH team, the analogy is clear and compelling. AlphaGo demonstrated that an AI could produce solutions that fell completely outside the realm of human intuition, yet still win. In the same way, they claim that ASI-ARCH has discovered neural network architectures that depart from established design principles, yet outperform strong baselines like DeltaNet and Mamba2 under matched computational budgets. This is the core of their AlphaGo moment claim. However, there's a key difference that separates this work from the historical significance of AlphaGo. AlphaGo's strength was proven in public matches, witnessed by a global audience, and played under widely accepted rules. ASI-ARCH's results, by contrast, exist only in experiments run by its creators, on the benchmarks they chose. Without broader, independent testing, it's unclear whether these designs will hold their advantage outside this controlled environment. This creates a critical point of tension. AlphaGo earned its place in history because its success played out in full view. ASI-ARCH's decisive trial has yet to happen. So, what evidence can the authors provide that their system's innovations are as groundbreaking as the moves of AlphaGo? Let's dive deeper into what ASI-ARCH really is to truly understand the system and the authors' claims. ASI-ARCH is designed as a multi-agent closed-loop research system. It operates as a continuous, self-improving feedback loop that mimics the scientific process, but at a speed and scale impossible for a human team. The system's core is its 3 coordinated AI agents, each with a distinct and specialized role. The researcher agent is the creative engine. It queries a vast cognition base that contains historical data from nearly 100 seminal papers on linear attention, a method for AI to focus on relevant information more efficiently. It analyzes this body of human knowledge and then, based on its findings, hypothesizes a new architectural concept, writes a brief motivation explaining the idea, and then generates the corresponding PyTorch code. This is where the system generates new designs, such as integrating components that are normally kept separate, a process that requires a form of conceptual creativity. The researcher agent also does a sanity check on any proposed architecture to ensure that it can be correctly implemented and goes through a validation process that ensures novelty. The engineer agent is the hands-on experimentalist. It takes the architectural code generated by the researcher and attempts to train it in a real-world environment. This agent possesses a robust self-revision mechanism. If the code crashes or if a training run encounters an unforeseen bug, the engineer analyzes the error logs, patches its own code, and retries the training run. This iterative debugging loop is a critical piece of the puzzle, ensuring that promising architectural ideas are not discarded because of simple coding mistakes, a common failure point of other automated systems. The analyst agent is the team's synthesizer and critic. After a training run completes, the analyst studies the performance metrics, training logs, and code. It compares the results not only to human baselines, but to the parent and sibling architectures within the system's own evolutionary tree. It then writes a concise report on what worked, what failed, and why, distilling key insights that are fed back into the central memory to inform the researcher's next cycle of innovation. To drive the evolutionary process, ASI-ARCH provides the agent with two distinct sources of knowledge for each subsequent design step: cognition, derived from accumulated human expertise, and analysis, generated dynamically from the system's own experimental history. This process repeats endlessly, iterating on promising directions while discarding weaker ones. In their paper, the team describes ASI-ARCH running an astounding 1,773 autonomous experiments over 20,000 GPU hours. The search followed a rigorous two-stage process. Stage 1 trained smaller models, about 20 million parameters, on a dataset of 1 billion tokens. Many architectural candidates were tested quickly in this initial phase to identify early winners. Then, Stage 2 scaled up the most promising designs to 400 million parameters, training them on up to 15 billion tokens, before then comparing them to baselines under matched compute budgets. This two-stage process is designed to find novel designs quickly and then verify their scalability. The evaluation included a comprehensive suite of language modeling tasks and zero-shot reasoning benchmarks. Baselines included strong human-designed models like DeltaNet, Gated DeltaNet, and Mamba 2. These benchmarks are widely accepted and provide a fair comparison against existing models. The system discovered 106 innovative state-of-the-art linear attention architectures. The team specifically highlighted designs that included unusual component fusions. Examples included PathGate FusionNet with its hierarchical path allocation, Content Sharp Router, where routing sharpness was adjusted dynamically based on token content, and HigherGateNet with its hierarchical gating to preserve path diversity. In Stage 2, some architectures showed consistent, if modest, gains over baselines. For example, on certain language tasks, the top ASI-ARCH models achieved an average score of up to 48.51 compared to the best human baseline's score of 47.84. While the gains may seem small in isolation, in a highly competitive field, even a fractional percentage point can be a significant breakthrough. The authors also highlight the novelty of the process itself rather than the size of the improvements. The system can produce architectures that beat strong baselines in controlled conditions, but the open question remains: will those results scale and generalize? One of the most striking and debated elements of the paper is the reported first empirical scaling law for scientific discovery itself. The authors plot the number of state-of-the-art architectures found against total GPU hours and observe an almost linear trend. This would suggest that the pace of architectural innovation could be increased simply by allocating more computation rather than more human expertise. This implies a profound shift in the core bottleneck of AI research, from slow human-led research to computational power, which is accelerating at a staggering rate. If this holds true, it could mean that the next great scientific breakthroughs in AI will not come from human insight, but from the automated experimentation of a machine with massive computational budget. However, scaling laws in AI are complex and can be deceptive. Previous work has shown that they can fail when data quality changes, when model sizes grow beyond the experimental range, or when research objectives shift. For example, the scaling laws observed in large language models often break down when the models are used for very specific niche tasks that were not represented in their training data. Without replication under varied conditions, it's unclear whether this relationship is robust or specific to the experimental setup. If the trend holds, research leadership could depend primarily on compute access. If it does not, the advantage may vanish in different contexts, providing the scaling law to be an interesting but ultimately limited observation. Another important counter-argument to the idea that more compute alone will always lead to better scientific progress comes from recent research by Anthropic. Their work suggests that giving AI models more time or more resources to think doesn't always result in better performance. In fact, in some cases, it can lead to inverse scaling, where models get worse at certain tasks the longer they reason. The research highlights several failure models, including models becoming distracted by irrelevant information, overfitting the problem's framings, or failing at logical deduction with extended reasoning time. This implies the linear scaling law proposed by ASI-ARCH may have limitations, and that AI progress also depends on factors beyond just raw computational power, such as data quality, reasoning strategy, and careful evaluation of a model's thinking process. Reaction to the ASI-ARCH paper has been divided. On one side, there are those who believe that this work represents a paradigm shift, and on the other, there are the skeptics who view its claims with caution. Some researchers object to its terminology, warning that terms like artificial superintelligence and AlphaGo moment for AI research may lead non-experts to believe the system has broader capabilities than it does. This kind of hype is a frequent concern in a field where promising research can easily be over-extrapolated by the public. Others focus on the experimental scale, noting that the results come from models much smaller than the largest in use today. For example, the largest models mentioned in the paper, at 400 million parameters, are dwarfed by models like GPT-4, which is estimated to have over 1 trillion parameters. A frequent critique is that the performance gains are modest and could be explained by randomness in initialization or training. In a field where minor variations are common, it's difficult to confirm that the advantage comes from the architecture alone without exhaustive large-scale replication. Supporters counter that the system's significance lies not in the size of its gains, but in its method. It's a fully automated pipeline that can propose and test ideas outside a human-defined search space. They argue that even small gains could matter immensely if they come from truly novel designs that humans might never have attempted. So, is this the early stage of a new research paradigm, or a narrow proof of concept that will never scale? That's the central point of contention, and it leads us to the fundamental implications of this work. And if you're enjoying this video, please leave a like and subscribe. I look forward to learning about science and engineering topics and diving into a new topic each week. Your support really means a lot to me and will help me continue this work. If ASI-ARCH's approach proves robust, it could shift the main constraint on AI research from human creativity to computational scale. The ability to run continuous, autonomous cycles of experimentation could accelerate discovery not only in AI, but across other scientific disciplines as well. Such systems might be adapted to chemistry, materials science, or medicine, where automated idea generation and testing could shorten the path from hypothesis to result. In a striking example of AI accelerating materials science, a collaboration between Microsoft and the Pacific Northwest National Laboratory used AI to drastically speed up the discovery of promising new battery materials. The project focused on solid-state electrolytes, a critical component for the next generation of batteries that are safer and more energy-dense than current liquid-based ones. Leveraging AI and supercomputing, the team screened over 32 million potential inorganic materials in just 80 hours, a process that would have taken decades through traditional methods. This initial search yielded 23 promising candidates, one of which was successfully synthesized and tested in a prototype battery. The material, a combination of lithium and sodium, was particularly significant because it was unconventional and could potentially reduce their reliance on lithium by up to 70%, addressing major supply chain and environmental concerns. The project demonstrated AI's ability not just to optimize existing designs, but to break from human-driven intuition and discover genuinely novel and effective solutions. If we extend this line of thinking, the implications become even more profound. What happens when these autonomous research agents begin to collaborate? A single ASI-ARCH system is powerful, but what if a network of these systems, each specializing in a different field, one for material science, one for quantum physics, one for biology, begins to exchange information and insights? This could lead to a cascade of cross-disciplinary breakthroughs that would be nearly impossible for human researchers to achieve in a lifetime. Imagine a system designing a new type of battery architecture, which is then immediately tested by a second system, and its properties are fed into a third system, tasked with designing new solar cell materials to maximize efficiency. The iterative cycles of discovery would accelerate exponentially, creating a new kind of scientific ecosystem. Based on the paper, the researchers claim that the AlphaGo moment refers to a pivotal shift in the field of AI research, moving beyond automated optimization to a new era of automated innovation. The paper argues that despite exponential improvements in AI, the pace of AI research itself has been linearly constrained by human cognitive capacity. The AlphaGo moment in this context is the first demonstration of a system, ASI-ARCH, that shatters this fundamental constraint by enabling AI to conduct its own architectural innovation autonomously. This transforms the velocity of innovation from a human-limited to a computation-scalable process. Just as AlphaGo's Move 37 revealed a strategic insight invisible to human players, the AI-discovered architectures in this paper demonstrate emergent design principles that systematically surpass human design baselines. The system discovers qualitatively different architectural intelligence that expands beyond human design paradigms and establishes new principles for innovation. The paper establishes a blueprint for self-accelerating AI systems. This includes autonomous, tool-centric, multi-agent frameworks that enable AI to conduct the entire scientific research process independently. This process is a closed evolutionary loop, handling every step from hypothesis generation to implementation as executable code and empirical validation. The system's ability to fix its own implementation errors in a robust self-revision mechanism is a key component of this. And a crucial foundational implication is the claim that the work established the first empirical scaling law for scientific discovery itself. The paper demonstrates a strong linear relationship between the amount of computation, GPU hours, and the number of novel, high-performing architectures discovered. This indicates that research progress can be scaled with computational resources rather than human expertise, providing a concrete pathway towards artificial superintelligence for AI research, ASI for AI. The success of systems like ASI-ARCH in accelerating scientific discovery raises a fascinating and potentially unsettling question. Could an AI discover something that a human cannot understand? This is a core challenge in the field, often framed as the contrast between black box AI and interpretable models. While some AI systems, like simple decision trees, can be easily understood by humans, the most powerful and complex models, such as deep neural networks, are notoriously opaque. We can see what they output, but we cannot see their internal reasoning. The unexpected moves of AlphaGo were eventually deciphered by human experts. But what if an AI designs a complex molecular structure or a fundamental theorem that is so counterintuitive, so far removed from our cognitive frameworks, that we can only verify that it works without truly understanding why? This would create a new kind of knowledge gap, where we rely on the outputs of a machine for progress, but we lose the ability to reason about the underlying principles themselves. This is the black box problem. It's the very problem that the field of explainable AI, XAI, seeks to address. XAI researchers are developing methods to provide insight into models' decision-making processes. The goal is to transform black box models into more transparent or at least explainable systems. And as we automate the process of invention, we must also build a new layer of oversight, one that is as agile and adaptive as the systems it's meant to govern. So, is this the start of the next scientific revolution? Is this really the AlphaGo moment for AI? The honest answer is, it's too early to tell. ASI-ARCH is a promising, even groundbreaking proof of concept, but it has yet to show the world-changing results at the kind of scale that would make it undeniable. The AlphaGo moment label will only stick if the designs it produces lead to clear, verifiable, and widely adopted advances in high-impact AI systems. It needs to prove its worth on the grand multi-billion parameter stage. In that sense, perhaps the most important thing ASI-ARCH has achieved is not a specific architectural breakthrough, but the ability to work through the scientific process itself beyond the bounds of human supervision. And it's forcing us to ask, if the very tools of discovery can make the discoveries themselves, what does that mean for the pace and the nature of future progress?